yeah, like we said yesterday, we discussed a lot about how variation between ingredients is really notable, and it has a direct effect on digestibility, bird performance, and bird uniformity. So at the moment, we're still struggling with handling this variation in feed formulating. And today I'm going to talk about how we can maybe use enzymes to help combat this issue. So before we start even thinking about putting enzymes in, we need to have a good understanding of what our undigested components in our feed is. So no feed ingredient is 100% digestible. So even things like starch, lipids, proteins that the birds have endogenous enzymes for, we're still looking at about 20 to 30% that is not digested, and it's just excreted, so that's wasting money. So yeah, we've still got that proportion that's undigested, and we have 3 different sorts of substrates that we need to think about. So we have our substrates that we have the endogenous enzymes available for, so the birds can use those. We have our substrates that the birds don't have the endogenous enzymes for, so they can't use them, so things like cellulose. And then we also have our substrates, as well as not being digested by and broken up by endogenous enzymes, they're also having anti-nutrition effects, so things like our phytate and our NSPs, and our beta-glucans and stuff. So when we're considering estimating how much of our substrate can be hydrolyzed by enzymes, we have a number of limitations. So first of all, we have coefficients of digestibility of many of our substrates are not available. So they're not in our NRC values, and they're also difficult to analyze. So for example, our NSPs, hard to analyze, so we don't have as much data as we do for substrates that are easier to analyze. Differences in how nutritionists approach their formulations. So often we think we're all meeting the same, trying to get the same energy and protein requirements, and we might even be using the same reference values. But as a nutritionist, how you're handling this information and what you come up with at the end is very different. So we're going to end up with different substrates. High variable feed ingredients. So globally, we've got a lot of variation between our feed ingredients. So generally, our lower cost feed ingredients have more anti-nutritional factors in, and our ingredients that are lower in digestibility tend to have more variation and be more variable. And I think the biggest one is at the moment we still don't completely understand the molecular structure of the substrates we've got, so we're not sure how to handle them with enzymes. So starch and protein that is not digested properly will reach the hindgut and will be fermented, and that will result in lower energy yield, and also these undigested components will feed the pathogenic bacteria. So the issue that we have with starch digestion and why it's incomplete, when we've got starch in pelleted form, it's not as easily accessible. So the birds can't access it as well in pelleted diets, but we're feeding pelleted diets. Also, our faster growing birds now are not as efficient at using starch as our slower growing birds were. So we've got that genetic component that makes them not as good at using starch. And yeah, we have changed the genetics of the bird too much now. With our protein and our amino acids, we've got an issue with the species and the gene variety of the ingredients we feed, and also an issue with thermal processing. So what happens when we heat them up is that, for example, when we're heating, we can get sugar moieties that bind to lysine and make it less available. So then we've got more undigested lysine in the tract that's not being used properly and can feed our pathogenic bacteria. So when we talked a bit about yesterday about microbiota, so these undigested components in the tract are going to make the microbiota proliferate. So then what happens is these nutrients are feeding the microflora, and they're acting as competition for the host. And we've also got how we're changing the structure of the digester. So the digester structure and the chemical components in the digester are going to be changed by our diet ingredients. So how our diet changes. The diet effects that we're having on the digester, the structure, the chemical composition, will determine what microbiota we're going to have in there. So we can use enzymes to modulate and mediate the microbiota. So we change it with the enzymes, and then we change the chemical composition, and that will change what microbiota are there. So one thing I've been working on in my research is developing a non-starch polysaccharide database. So I've been measuring the soluble and insoluble NSP levels in different ingredients around Australia. So these values here represent at least 15 different samples of each feed ingredient. So this shows you how much range we've got in soluble and insoluble NSP. So as you can see, it varies quite a lot. And we need to consider both the soluble and the insoluble NSP because they have different anti-nutritional properties. So our soluble NSP mainly is concerned with viscosity, whereas our insoluble NSP acts as a diluent, so it dilutes our diet down, and it also has a caging effect, so it traps nutrients in it, so then they're not able to be utilised. So corn and wheat cells have pretty much the same cell wall structure, but just their NSP content's very different. So wheat has a lot more arabinoxylan and beta-glucan, so that's why we have a lot more viscosity issues with wheat than we do with corn. So just to put it in context a bit, a typical wheat soybean meal diet has approximately 9% NSPs in it, and 47% of this 9% is made up of xylan. In a corn soybean maize diet, we're looking more at about 6% NSP and about 43% xylan in it. So when we think about NSPs, we mainly often think about viscosity, and when we're putting in NSPases, it's often a main focus. So how it works with viscosity, so it's our soluble NSPs that are causing these viscosity issues, and mainly arabinoxylan and beta-glucan. But we focus more on arabinoxylan because, like I just showed you, there's more of it in the diet, and also it's comparatively more resistant. So we worry more about arabinoxylans. So what happens is these soluble NSPs, they thicken the rate-limiting unstirred water layer in our mucosa. So then that prevents nutrients being diffused and then being absorbed. So in response to this, we also have more undigested nutrients in the tract. So then we've also going to have more mucin secreted because our undigested products cause fermentation and they stimulate the microbes that then stimulate the mucosa, so then we get more mucin present as well. And then due to a change in the oxygen tension in the tract, that's when our fermentation happens. So when we think of viscosity and soluble NSP, we usually mainly focus on its physical effects, so how the soluble NSP is physically changing transit rate and ability of us to stir it. But actually this overgrowth of microbiota is equally as important as the physical effect of viscosity. So when we're putting in enzymes to combat viscosity, we're also manipulating the microflora, so that we're feeding the beneficial flora and not so much feeding the pathogenic ones. So we're still not completely clear exactly the relationship between viscosity and the microbiota, but we think it's mainly to do with this effect on oxygen tension and changing the oxygen levels within the tract. So in that way, we're changing the environment from being aerobic or facultative anaerobic, to just anaerobic. So that'll change what microflora can flourish because it depends on what environment they're cooling. And this was an interesting study that I read recently. And what they did is they fed conventional birds and germ-free birds NSP. So they used highly methylated citrus pectin as a source of NSP. So they were giving the birds the same diets, the same NSP levels. And the effect on viscosity was exactly the same in both birds. But it was only in the conventional birds that this translated to an effect on digestibility, nitrogen retention, and performance. So this suggests that it isn't just the viscosity itself that is causing the problem. It's this idea that changing the viscosity in the oxygen levels in the digester is changing what microflora you've got, which we talked about yesterday. So yeah, when we're talking about our soluble NSPs, we should be thinking more about its impact on microbiota and not just physically on its effect in the tract. Also, in some of the research we've been doing, we've seen that viscosity tends to increase until the birds reach about 21 to 28 days, and then not so much an issue. So this suggests that as the bird ages, it's able to change insoluble NSP into soluble NSP. It's able to solubilize it. So as it grows, we have more soluble NSP present in the tract that's causing our viscosity issues. But then at this age, the microbiota isn't then also able to convert it again into useful products. So it's not until about after day 21 to 28 that the bird's microbiota is adapted to be able to use this soluble NSP well. So again, this illustrates that with viscosity, it's about the microbiota. And this suggests that maybe in older birds, we're able to use more viscous grains more. We can use them more and not worry so much about the physical effects of viscous grains in older birds. And it also suggests that when we're putting xylanase into grower and finisher diets, that the focus isn't on changing the viscosity so much. It's more to do with this act of breaking up our long-chain xylans into our smaller oligosaccharides and how the birds can use those as a prebiotic. So yeah, suggests maybe we should be looking at it from a different angle when we're putting xylanase into diets in older birds. So obviously at the moment, due to feed costs, there's a big interest in using alternative feed ingredients. Now the issue at the moment that's hindering this is being able to characterize their nutritional value. So particularly when we're looking at NSPs, and it's very costly and difficult to analyze NSPs. Using what technologies we can use on our ingredients to mitigate the risks, so mitigate our anti-nutritional factors and our mycotoxins and that sort of thing, and also the economic benefits, so being able to formulate with these alternative ingredients so that you're getting cost benefits. So this is where our NSPases can come in. So the potential to use alternative ingredients is increased when we're able to combat these issues using enzymes. So then, once we've got it locked down what's actually our undigested components are and what our issues are, then we can go on to step 2, which is selecting our enzymes. And it only makes sense to use an enzyme if you know that you've got the substrate in the diet and you know that's what's going to result from the enzyme substrates together is going to be absorbed and used by the birds. So it's this indiscriminate use of enzymes that is making us have inconsistent results. So yeah, when we think about the value of enzymes, another issue we have is that we need to divide the value between what cost benefits we're going to get and also what bird performance we're going to get. So just looking at the cost benefits alone when using enzymes is where we end up with inaccurate formulations using them. So we need to put value on both bird outputs and also how much cost in feed we're going to save. So when using our enzymes, we think about their different modes of action. So first of all, their ability to hydrolyze chemical bonds to make our starch, lipids, proteins, etc. more available. We want to eliminate our nutrient encapsulating effects. So, for example, with our insoluble NSP, so like I said, our insoluble NSP traps nutrients in the matrix. We want to release them. So we use enzymes to get rid of the insoluble NSP as well. And that's a big thing. When people think about NSPases, they're mainly focusing on just the soluble NSP and these viscosity effects. But the insoluble NSP is also equally important, if not more sometimes. So we also need to be thinking about how we can get rid of this cage effect of our insoluble NSPs. Breakdown of anti-nutritional factors, for example, our phytate and our phytases together. Like I said, we want to be able to solubilize our insoluble NSP, because if our NSP is soluble, it means that it can be fermented in the hindgut and provide energy. So we want to try and solubilize our insoluble NSPs. And also this idea of using enzymes as a complementation in young animals. So young animals that don't have enough amylase and protease and lipase, we're giving them it. So yeah, as bird ages, their release of pancreatic amylase gets less and less. So when we actually need lots of amylase is in the grower and finisher phase, and that's when the bird is actually making less of it. So we need to think about how age impacts what enzymes are available. So there's often this thought that using enzymes means that we're increasing the quality of a low quality ingredient, or we're reducing the amount of difference between a low and high quality ingredient. And they do, but it's really not as simple as that. So there's a lot of factors that we need to consider when we're thinking about our substrates, if we want to be able to increase the precision of our feed formulations. So it's not as simple as just here's the substrate, here's the enzyme. We need to be thinking about the location of the substrate within the ingredient matrix, its solubility, any other limiting factors there are, and its accessibility. So this whole concept of how susceptible your substrate is to your enzymes. And as well as just thinking about that, we also, like Rick talked about yesterday, think we need to consider the quality of the birds. So a poor quality bird is going to react more to an enzyme than a high quality bird, because we're changing the microbiota for the better. So yeah, our low quality birds are going to respond more. So if you've already got really good birds, then you're not going to see as much of an enzyme effect. And pretty well known, but enzymes must also be accompanied by a change in the feed composition. So if your diet's already really high in energy and protein, it's this idea of the cup's already full. You're not going to get more out of it. So we need to manipulate the diet so that we can get the full benefits of the enzymes. So this is where we have to apply our matrix values. So we work out how much extra digestibility we're going to get from our enzymes, then reduce the protein and energy of our diets, and then put our enzymes in, because otherwise we're not going to get any cost benefits from using our enzymes. And the whole idea is that they're helping us use the protein and energy from the diet better. So yeah, we need to, when we're putting in enzymes, also think about how we need to manipulate the feed so we're actually getting cost benefits of using it. And it's very rare just to stick an enzyme on top of a diet, because we're not going to achieve it. So we need to assign it its own nutrient value. So with most enzyme substrate relationships, we can measure the substrate that's in the diet, we can put the enzyme in and measure what comes out. But this isn't possible with NSPs. And this is to do with how complex they are, how much variety there is in NSP between different ingredients. Like I said, how susceptible they're going to be to your enzymes, how exposed they are, so how easy it is to access them. And yeah, we can't measure its conformation as well, so we can't measure exactly what substrates we're going to get as a result. So then that makes people get a bit confused with NSP enzymes, you can't measure exactly what's coming out. So yeah, so how exactly are we going to measure it? So what we need to do is we need to elucidate the molecular structure of our polysaccharide fractions that come out. It's the only way we can really do it. So we can look at what polysaccharide fractions we've got coming out at the end, and then just rely on all the other measurements in the VADs that we usually do. So I've been doing some research as well as the NSP database. I've also been working a bit on a database of xylan levels in feed ingredients. So again, these are the means from at least 15 ingredients, 15 different batches of each ingredient. And you can see why, basically this is illustrating why xylanase works in both corn and wheat. So with wheat, we have pretty high insoluble xylan. So like I said, the insoluble xylan is the ones that's trapping our nutrients. And we've also got pretty high soluble xylan. So we've also got these viscosity effects. So that's why xylanase works so well on wheat, because we're combating both issues. With corn, however, we know corn doesn't cause any viscosity issues because it's got barely any soluble NSP and barely any soluble xylan in it. But it's got really high insoluble xylan. So when we're putting xylanases in corn-based diets, this is what we're focusing on. We're focusing on getting rid of this cage effect of our insoluble NSPs. And this was just, so I did a completely unrelated study. It was an AME study with 7 different diets. But I just fancied measuring the xylan in them. So what I thought was interesting from measuring the xylan, so these were just completely, they were formulated to be pretty much the same, but completely different ingredient levels. So they had different xylan levels. But what was interesting is that for the soluble xylan, we're getting pretty high digestibility by the ileum. But with our insoluble xylan, we've got as low as 4% of it being used. So these diets didn't have any xylanase in. So again, this illustrates that our focus is usually always on combating viscosity, but really it's this insoluble xylan that we can be getting all the benefits from putting xylanase in. So like I said, to be able to, we need different ways of being able to measure the outputs from putting our enzymes in. So one way I've been looking at measuring how good our xylanases are working is to measure these smaller size fractions. So we've got our long xylan and we're crunching it up with our enzymes, and then I've been looking at the smaller oligosaccharides. So the idea is, I'll talk about it in a minute, but these oligosaccharides can be used as prebiotics. So we're putting xylanase in the diets anyway to try and combat all these nutrient viscosity things, but we're also getting this added bonus of these prebiotics that are coming out of it. So what I did in this study is I just took wheats from different areas, different states around Australia. And for those of you that haven't been to Australia, it's such a huge country that everywhere has pretty much different weather. So we've got different growing conditions in all the different states. So for example, in Queensland, it's pretty tropical and humid, whereas in West Australia, it's a bit more dry and deserty, and then South Australia is pretty grey and rainy. So we've got completely different growing conditions in all these different areas. So I took 10 different batches of wheats grown in all these different areas and just slapped some xylanase in with them and measured the oligosaccharides that came out using GC-MS. And what was interesting is just how different the amount of oligosaccharides was that was coming out, and also which size they were. So we think for poultry, for this prebiotic effect, we're mainly aiming for X2s and X3s, so xylobios, 2 xylose units together and 3 xylose units together. But we're working on that moment to work out exactly what size they like. What wheat examples we use will determine what oligosaccharides would come out in the presence of xylanase. So this is why we're not always getting the same consistent effects with putting xylanase in 2 different diets. And there's also this focus on reducing, as a way to reduce variability, using the idea of phytate-free nutrition. So like we talked about yesterday, this idea of superdosing. So if we can get rid of all the phytate in the ingredients, then we're at more of a level playing field with them, because they've all got no phytate in. So yeah, putting superdoses in so we can get rid of pretty much all the phytate, and also get the added benefits of our myo-inositols. So they've been shown to help with translocation of GLUT4 transporters and have insulin type effects. And also, like we talked about, phytate has an impact on protein digestibility, so it increases mucin secretion and nitrogen endogenous losses. So if we've got rid of the phytate, then we can also improve protein digestibility. So again, we can reduce the variability a bit with our protein digestion. And also, there's interest still into alkaline phosphatases. So using them to break up the lipopolysaccharides in the membrane of our gram-negative bacteria, which has an impact on improving nutrient utilization. So going back a bit to the prebiotic oligosaccharides, so again, this is something I'm super interested in at the moment, and I ran a little pilot study where I fed arabinoxylans, xylo-oligosaccharides that I'd made in the lab and fed, or arabinoxylans and xylanase together. So basically I was trying to compare if it was better for me to make the oligosaccharides in the lab and feed them to the chickens, so the work's already done for them, or if they're better at making them themselves. And 2% is really high. We wouldn't ever normally put 2% in. We'd put, tiny amounts in real life, but I just wanted to make sure that we could see what was going on clearly. And what we found was that we did have improvements in short-chain fatty acid production as a result of our oligosaccharides. But what was interesting is for all the individual short-chain fatty acids, there was always a consistent difference between feeding arabinoxylan and feeding the oligosaccharides that I'd made in vitro, but there wasn't always for when the birds make it themselves. So this suggests that the birds can use them better if we make them for them. So it highlights the potential of making oligosaccharides as a feed additive, as a prebiotic additive. And it wasn't significant, but we saw increased lactobacillus levels as well, which suggests that the birds were able to use them and improve, and it manipulated the microflora. So other studies have also shown that these xylo-oligosaccharides can improve colon function, immunity, villus length. So it's a pretty hot topic at the moment, and it looks quite promising. So again, this highlights the added benefit of putting in our enzymes, because we're getting these added benefits of these prebiotics coming out. And we can also use enzymes to help us with diseases. So it's well known that more insoluble NSP means more viscosity in the tract, and more likely that we're going to have issues like necrotic enteritis, because Clostridium perfringens favour soluble NSP. And also, like I said at the very beginning, we've got more undigested nutrients in the tract because of this. So especially amino acids, the Clostridium perfringens love eating amino acids. So if we've got more undigested amino acids in the tract, then they're more likely to flourish. So Mingen found this when he put xylanase into wheat-based diets and saw that it made Clostridium perfringens not present. And people have also seen similar with Salmonella. So once we've sorted out what enzymes we need, we can then go on to start developing enzymes more. So we haven't harnessed the full potential of enzymes yet. So even in really digestible corn soy-based diets, we've still got 10-15% of undigested products in them. And yeah, so at UNE, one of our students has recently done a study and we found as high as 33% in wheat-based diets that's undigested. So there's still a lot of potential, and we can't ever get 100%, but we expect our enzymes to be able to break up at least 20 to 30% of this undigested material. So when we're developing the enzymes, it's important to define exactly what we want it to do and under what conditions, so where in the gastrointestinal tract that we want it to be working. And the biggest issue we have is assays to measure them. So this is also an issue in a lot of journals that I've found. It's hard to see how much activity their enzymes had, or sometimes even what family of enzymes they used, and yeah. So there's often not a lot of detail in journal articles about the enzymes themselves. But when we want to develop a new assay, we need to consider the balance between how well it represents what's going to go on in the bird, and also the costs associated with it, and the throughput, so how difficult it is to do. Because if you want to be able to do it on farm or whatever, it needs to be easy and cheap to be able to measure what's going on with your enzymes. And the process that we go through is that first the enzymes will be tested in vitro, then tested in animals, and then we need to ensure that it's stable in the entire distribution feed chain. So we need to make sure that it's fine with being stored, that it's fine, it's good for that we can formulate with it, and that it can be fermented so we can make large batches of it. We also need to determine the optimal production process. So how we're going to make it, what's our best way of doing it, how we can ferment it, how we can produce it. And also how are we going to be able to formulate with it. So as we know, there's a lot of interest in enzyme cocktails. So often people in wheat, soy-based diets just think about putting xylanase in. But like I said, there's a lot of other NSP products in there as well that could benefit from having cocktails of enzymes. So yeah, we should be thinking more about getting the most out of all our NSPs, not just our xylanases. And also looking more at phytases and NSPases together, which we're doing quite a lot at the moment. So for example, in this study by Cowison and Adiola, they had a marginally deficient corn-soy diet, so slightly low in metabolizable energy, calcium and phosphorus. And then they either fed xylanase, amylase and protease together, XAP, or phytase, or they put them all together. So when they had them as two separate treatments, they saw about 6 to 7% improvement in body weight. But when they put all 4 enzymes together, they saw 14% improvement. So pretty much doubled by putting them all together. So yeah, we're doing a lot at the moment looking at cocktails, but we also need to consider maybe the negative effects of putting them together as well. So maybe when we put them together, they're not making the substrate ideal for each other, and consider what levels we want to put them in so that they work really well all together. So this is some information that Adeseo gave me, showing how they use their Rover Bio products. So here we're looking at a cocktail of xylanase, beta-glucanase, pectinase, and mannase together. And here in the top graph, you can see that we had 3 different types of wheat, They all had different AME levels to begin with, but when you put the enzymes in, they're all pretty much the same. So this shows how we can use enzymes to reduce variability. In this graph below, they fed 60 birds with the enzymes, 60 birds without, and observed the number of birds that had the same AME. So as you can see, putting in the enzyme meant we had more consistency, so there was less variation within the flock about how much AME they had. And similar with protein digestibility. So they fed either a classic diet, so just a wheat, soy, full-fat soybean meal diet, or a complex diet. So it had those 3 ingredients, plus rapeseed meal, sunflower meal, wheat dedigest, barley, and rye. And they found that when they added the enzyme to the complex diet, it made digestible protein similar to our classic wheat soybean diet. So that suggests again that we can be using more alternative ingredients, and yeah, we can be using more variety of ingredients if we're coupling it with enzymes. So it helps us open our doors to more ingredients. So in conclusion, the gain in improving variability we can gain from enzymes is we can neutralize our anti-nutrient effects. We're releasing nutrients from our indigestible components, which are causing us a lot of issues at the moment, and then produce bioactive nutrients, so for example our oligosaccharides, from these components. Thank you very much.